This is Radhika. I am going to discuss about the power electronics subject. This is for electrical 5th sem students. So now, in last classes we discussed about the single phase half wave control converter using R load. So using of R load of single phase controlled converter, we discussed the working and waveforms of the output voltage and output current of the single phase half wave controlled converter using R load. So today we are going to discuss about the single phase half wave controlled converter using R load, and also we are going to discuss about the freewheeling diode and using of RL load. So these are the today our topics. Next, this is the diagram for single phase half wave control converter with RL load. So here in this diagram it shows the single phase half wave control converter using RL load. It consists of a single thyristor feeding DC power to RL load. Let us consider a source voltage Vs is equal to Vm sin omega t is applied to the circuit. So in this diagram, this is the input voltage, supply voltage is equal to Vm sin omega t, and this is the thyristor. It will converts AC to DC, and here we are using the RL load. The output is V0. So in this these are the waveforms for single phase half wave control converter using RL load. So in this it shows during the positive half cycle of input voltage, the thyristor anode is positive with respect to its cathode. Hence the thyristor is said to be forward biased. When the thyristor is triggered at some delay angle omega t is equal to alpha, the thyristor starts conducting and full voltage is appeared across the load as V0 output voltage. But the inductance L forces the load current I0 to rise gradually. After some time, I0 reaches maximum value and then begins to decrease. So here this is the supply voltage. First waveform is the supply voltage. It is normally sine wave, and next is the load voltage across the thyristor. That is the output voltage, and output voltage as this is the firing angle alpha we discussed in last class. After some delay angle, it goes the maximum voltage and it falls to negative half cycle, because we are using the inductance. And here this is the output voltage. This is the output voltage. The current will be conducted to the alpha to pi plus alpha. The cycle will be repeats. So where the output voltage appears the waveform in thyristor voltage, that will be disappear here. Means when we are using the voltage in output voltage, means the period conducting in output voltage, the remaining time will be appeared in thyristor waveform. So here at omega t is equal to pi, V0 is 0, but I0 is not 0 because of the load inductance L. After omega t is equal to pi, thyristor is subjected to reverse anode voltage, but it will not be turned off as load current I naught is not less than the holding current. At some angle beta greater than pi, I naught reduces to 0 and thyristor is turned off as it is already reversed bias. So alpha after W2 is equal to beta, here is the beta point is here, the beta point is 0 to pi, B output is equal to 0 and I naught is equal to here 0. At omega t is equal to 2 pi plus alpha, thyristor is triggered, triggered again, V naught is applied to load and load current also repeated. The angle beta is called extinction angle and beta minus alpha is called, that is gamma, that is conduction angle. Yeah, beta is the extinction angle and gamma means beta minus alpha. Gamma is the conduction angle. The wave of voltage across the thyristor Vt during the conduction periods, the voltage drop across the thyristor is 0, and during the non-conducting periods, the voltage drop is the thyristor is appeared and it's shown in the waveform. So here this is the only discussion of waveforms of single phase half wave controlled converter using of RL load. So in this RL load, so this is the diagram. So in this supply voltage, source voltage, average voltage across RL load, and IS is the supply current, I naught is the average load current, and V is the voltage, it is the thyristor voltage. And here we know that the load current I naught is in phase with load voltage V naught for pure resistive. So already we discussed in previous classes, in case of pure resistive, the current and voltage will be in phase. But when the load is RL, the situation becomes different and load current does not assumes the waveform of the load voltage, and the load current lags behind load voltage by an angle. So these are the waveforms, and in this at omega t is equal to alpha, thyristor is turned on by gate signal. Thyristor conducts so that the load voltage is equal to supply voltage. Load current will commence directly, the supply voltage goes positive, but the presence of the inductance will delay the current change. So at omega t is equal to pi, V naught is 0, but I naught is not 0 because of load inductance. From omega t is equal to pi to beta, thyristor is subjected to reverse anode voltage due to the voltage stored in the inductance oppose the supply voltage. But the thyristor will not be turned off as load current I naught is greater than the holding current. So here at some angle beta greater than pi, I naught reduces to 0 and thyristor is turned off as it is already reverse bias. So this discussion will be about the waveforms of the single phase half wave controlled rectifier with RL load. Okay. So Next is the these are the waveforms are single phase, half wave, fully controlled converter with the RLO. And from waveforms it is clear that load current is driven by load voltage from alpha to pi. From pi to beta the load voltage is negative and load current is maintained by inductance L. After omega t is equal to beta, V naught is equal to 0 and I naught is equal to 0. At omega t is equal to 2 pi plus alpha, thyristor is triggered again, V naught is applied to the load and the load current develops as before. So here beta is called as excitation angle and beta minus alpha is equal to gamma is called conduction angle. Waveforms of Vt reveals that when omega t is equal to alpha, Vt is equal to Vm sin alpha. From alpha to beta, Vt is equal to 0 and at omega t is equal to beta, Vt is equal to Vm sin beta. As beta greater than pi, Vt is negative and therefore thyristor is reverse biased from beta to 2 pi. And these are the equations of thyristor reverse biased for 2 pi minus beta radians. The circuit turn off time is Tc is equal to 2 pi minus beta by omega in seconds, where omega is the 2 pi f and f is the supply frequency in hertz. Already we know about this one. And these are the average load voltage and average load current. The average load voltage is equal to 1 by 2 pi integral of alpha to beta Vm sin omega t dWt. So after calculation of this equation you will get Vm by 2 pi of cos alpha minus cos beta, and the average load current I naught is equal to Vm by 2 pi r into cos alpha minus cos beta. So this is the about single phase half wave controlled rectifier with RL load. Now we are going to discuss about the freewheeling diode, and next the circuit is using a freewheeling diode we can connect a single phase half wave controlled rectifier with the RL load. So actually what is the freewheeling diode? As in the case of single phase half wave converter with RL load, the waveform of load current is not continuous, and due to this the operating power factor of the system becomes very poor, which may give rise to poor performance of the circuit. So here, in case of the single phase half wave converter with RL load, the waveform of load current is not continuous, and due to this the operating power factor of the system becomes very poor, which may give rise to poor performance of the circuit. In order to improve the waveform of the load current I naught and power factor of the circuit, a diode is connected across the load and is called as freewheeling diode. It is also called bypass or commutating diode. So freewheeling diode can also be called as bypass diode or commutating diode. In the case of single phase half wave control converter with RL load, the waveform of load current is not continuous. For improving the waveform of load current, a freewheeling diode is connected across the load. So actually what are the functions of freewheeling diode? One is to prevent the thyristor from reversal of load voltage V0, and also the other to allow the thyristor to regain its blocking state at the voltage 0 by transferring the load current I0 away from the thyristor. So using of the freewheeling diode, we have the continuous flow of the current. So we have the few advantages of freewheeling diode, that are waveform of load current is improved, means it is the in continuous form, and power factor of the circuit is improved, performance of the circuit improved, load performance is better, that is the freewheeling diode prevents the load output load and from the becoming negative. Now we are going to discuss about the single phase half wave control converter with RL load using a freewheeling diode. In before freewheeling diode, we discussed about the single phase half wave control converter with RL load, but same circuit we are connecting the freewheeling diode. So this is the freewheeling diode, means it is the bypass, the current bypass through freewheeling diode. So this is the same circuit for the single phase half wave control converter for RL load. So just we are using the only freewheeling diode. So in this also same explanation, but the waveforms are different. In this, we have the source voltage Vs, average voltage across RL load V0, supply current Is, average load current I0, and current through freewheeling diode IFD, and Vt is the voltage across thyristor. So this is the waveform of single phase half wave controlled converter using a RL load with freewheeling diode. So here the difference between normal RL load and RL load using of diode, freewheeling diode, here the output current will be, it is in continuous, it is not in break form. So that is the difference between using normal RL load and RL load with using a freewheeling diode. Only that is the difference. So here in this, the working principle everything same, but the source voltage Vs is becoming positive, and at the some delay angle alpha, the thyristor is triggered, hence the source Vs is appears across load as V0 output voltage at omega is equal to pi. The voltage source Vs becomes 0, and after it tends to reverse, the freewheeling diode is forward biasing through the conducting thyristor. As a result, reverse. At the same time, the thyristor is turned off at omega t is equal to pi until the thyristor is again triggered at omega t is equal to pi 2 pi plus alpha. The load current I0 will flow through freewheeling diode. So this is the waveforms for RL load using of freewheeling diode. So this is the discussion about the single phase half wave control converter with RL load using a freewheeling diode. So these are the few advantages of freewheeling diode. And now, so we discussed about the single phase half wave control converter with RL load and using a freewheeling diode. Now we will watch the one YouTube video about single phase half wave control converter using of RL load and using of freewheeling diode.
Hi all, today we are going to discuss about single phase half wave control rectifier with RL load, and followed by we will discuss about what will be the need and effect of adding the freewheeling diode along with the RL load. So let us start with simple RL load. There is a source which is given by Vs is equal to V maximum sin omega t, which is following a sinusoidal wave like this, and it is connected to the RL load through a thyristor. Let us assume the voltage drop in the reference direction of the current passage across thyristor is plus minus as Vt, and the voltage drop across your load in the reference direction of current is plus minus here V0, and the current that is passing through your load is I0, and the current supplied by the source is Is. And now in the thyristor, because during positive half cycle we can decide from what instant it will start conducting. That means at what instant it will start conducting. Let us assume it is fired at a firing angle of alpha. That means this at omega t is equal to alpha, SCR is turned on by the firing pulse. So when the SCR is turned on by the firing pulse, this will act as a closed switch. So we can write the KVL in this loop. KVL in this loop will be equal to Vs will be equal to VL. Vs will be equal to V0, you agree with me? Or we can tell that Vs is equal to, that V0 is containing two parts, one is I0 multiplied by R plus L into dI0 by dt. Let us see the derivation for each components of the currents and the voltages. After that we will proceed further for the waveform, so that it will be more clear. So this Vs is a sinusoidal voltage. So this equation can be solved by using two things. That means I0 will be the sum of the steady state component plus transient component. So why this transient component is coming? Because it is coming mainly because of the inductor. Inductor will neither allow the sudden rise in the current or the sudden fall in the current. So it will create the transients. After some time the effect of inductance will go. So this transient component will become equal to 0, and the steady state component is the component once the system is stabilized, which depends on the time constant of your circuit, which is decided by the amount of L and the R. So this will be the steady state value. So the steady state analysis we have already seen in the basic electrical engineering. So you have seen that Is will be equal to, that steady state current is equal to V maximum by Z into sine of omega t minus phi. This phi indicates how much your current is lagging behind your voltage, because it is the inductive load, so always it will be lagging behind the voltage by some angle. So this angle is decided by tan inverse of omega L divided by R, where omega is equal to 2 pi f, and this Z is called as the impedance. That impedance will be equal to square root of R square plus omega L square. So this you have already seen there. Now coming to the transient component. To analyze the transient component, we can easily analyze from the source free equation. That means when your source is equal to 0, that means Vs is equal to 0, I can write that equation as I into R plus L into di by dt. I am doing the transient analysis, that's why I have represented with the suffix t. So I can apply the Laplace transform to this. This will become equal to 0 is equal to R into it of s plus L into S into it of s minus initial value of the current. So this initial value of the current component I don't know, so that I am representing by A. We are going to derive it from the boundary conditions later on. So I am taking it as A. So when you are taking this as A, this equation becomes R plus Ls of it of s is equal to, this L will go inside, this A is there, L into A I have taken to the right hand side, I have taken to this side. So from this I can write it of s is equal to, if I am taking L common, this will become R by L plus S, L will cancel, so this will become S plus R by L. So from this I can calculate it is equal to A into e to the power of minus R by L into t. I have calculated the inverse Laplace transform. So I can just combine these two components of the current. I can write the equation number 1 will be equal to I0 is equal to steady state component plus transient component. Steady state component is V maximum by Z sine of omega t minus phi, and the transient component is A e to the power of minus R by L into t. You can see here with respect to the time, this component, the magnitude value, initially it will be A, it will go on decaying gradually and finally it becomes 0. That means the transient component will die out with respect to the time. So now we can obtain the value of A by applying the boundary conditions, as we are triggering our pulse at omega t is equal to alpha. So at that time your thyristor will turn on or your load is connected to source. But the problem with the inductor is inductor will does not allow sudden change in the current. That means automatically at that instant the current, because it is in the relaxed condition, the value of I naught is equal to 0 at omega t is equal to alpha. So I am substituting in equation number 4. When you substitute this in equation number 4, I naught is equal to 0. This will be equal to V maximum by Z into sine of this omega t is nothing but alpha. This is alpha minus phi plus a e to the power of minus r by L into time, because omega t is equal to pi, t will be equal to alpha by omega. So the same thing I have substituted here, I got this one. So from this I can calculate my value of a is equal to minus V maximum by Z into sine of alpha minus phi e to the power of r by L into alpha by omega. Because this e to the power, so this will come divided by here. So 1 divided by e to the power of minus a, I can take to the numerator as e to the power of a form. So that form I have taken here. So this is the final value of a. So now I am substituting this a in the value of I naught. So I naught we got as V maximum by Z sine of omega t minus phi. That means one component is trying to follow the sinusoidal waveform, but another equation is there which is trying to suppress it. So that is given by V maximum by Z into sine of alpha minus phi e to the power of minus r by omega L into omega t minus alpha. So minus r by omega L into e to the power of omega t minus alpha. So at the instant alpha is equal to 0, so at the instant of alpha the I naught will be equal to 0. So what will happen if you plot the equation for this one here? So I am just plotting the curve for the current. So current, how it will start? At alpha, at the instant alpha, the current will start rising. So the current will gradually rise like this. It will reach up to the peak, then it will start falling. So let us assume it becomes 0 at an instant of beta. It will become 0 at an instant of beta. So when the current becomes 0, so automatically when the current is less than the holding current, your thyristor will turn off if your voltage is reverse biased. So you can see here, if you are plotting the output voltage will come like this. At this instant it is turned on, and the output voltage will continue as long as your thyristor is on, right? So the thyristor is on up to the value of beta, up to beta. So then your thyristor will be off. So your output voltage will be off because at this instant, or otherwise voltage across the thyristor will be from 0 to alpha. The thyristor is acting as an open switch, so entire voltage will drop across it. Again from beta onwards, it will again act as a reverse biased. So from beta it will again get reverse biased, and it will be reverse biased up to the instant of 2 pi. That means it is reverse biased from beta to 2 pi. After that it is in forward blocking condition from 2 pi to 2 pi plus alpha. Up to this instant the thyristor is blocking. So this way it will come. So again output voltage will be here. Again it will continue like this. Again it will continue up to beta. So similar is the case the current. So current again it will start from here, it will reach some peak value and it will fall down like this. So this is my output current, or which is equal to the source current. So let us proceed further. So the SCR conducts from alpha to beta. So here alpha is called as the firing angle, that beta the current is becoming equal to 0, that is called as the extension angle. So you have to calculate what is the value of beta at which this equation will be equal to 0. We can solve for the value of beta. So how to get this one? At omega t is equal to beta, we know again the boundary condition I naught is equal to 0. So substitute I naught is equal to 0 and omega t is equal to beta in this equation. So you will get this equation. So if you solve this equation, you will get the value of beta. So that is the beta which is called as the extension angle. So that beta value can be anywhere between pi to 2 pi. It depends on how much value of the inductance is there. It depends on that one. So I have taken the case of non-continuous conduction mode. That means beta is little greater than pi in this example. So continuous conduction mode we are taking for the case of freewheeling diode. So there that equations also will be covered. So now that value of beta minus alpha, that means the current is conducting from alpha to beta. So that means beta minus alpha, for this much duration your current is conducting, or the thyristor is conducting, so that is called as the conduction angle. So here the conduction angle is beta minus alpha. For this much duration your thyristor is conducting. So the same thing I am representing here in the current wave. Let us go back here. So this conduction angle is this much. So this much is your conduction angle. Conduction angle is this much. So let us proceed further. So now coming to proceeding further, at I naught is equal to 0 at beta, because I naught will be 0 at beta, so automatically thyristor is turned off and gets the reverse biased. So thyristor is reverse biased from omega t is equal to beta to omega t is equal to 2 pi. After that it will be forward biased, but it will act in forward blocking mode up to 2 pi plus alpha, but actually it is reverse biased from beta to 2 pi. So it is not conducting also, it is reverse biased. So the circuit turn off time is defined as the duration for which your thyristor is reverse biased, that means non-conducting mode, and in the blocking mode, that means reverse blocking mode, that is equal to, because it is from beta to 2 pi, so we can tell it as 2 pi minus beta, that is the duration, divided by omega, because omega 2 is equal to 2 pi minus beta. So Tc is equal to 2 pi minus beta by omega. So for satisfactory commutation, this value of this Tc should be always greater than Tq, which is called as thyristor turn off time. It is a time the thyristor takes to completely relax and the recombination of the carriers can happen inside. So it will again regain its strength. So that will be mentioned in the data sheet. So as per the data sheet, we have to take care while designing the circuit, converter circuit, your Tc should be always greater than Tq. Then only satisfactory commutation is possible. So now calculating the average value of the load current, we know that the output voltage is coming from alpha to beta, we have seen there. So out of 2 pi, so that's why it will be 1 by 2 pi. Integration from alpha to beta, V maximum sin omega t d omega t, this is V maximum by 2 pi into, if you substitute this, you will get it as cos alpha minus cos beta. So average value of load current I can calculate as average load voltage by resistance. Similarly, RMS value of the load voltage will be, out of 1 by 2 pi, it is conducting from alpha to beta, that value V naught square d omega t, V naught is nothing but Vs, so it is V maximum square sin square omega t d omega t whole to the power of 1 by 2. If you substitute, you will get this value. No need to mug up any formula, because we can easily derive in the exam if you understand the concept. So similar way I can calculate for the case of RMS value of current also. We know the value of I naught, so take the value of I naught square d omega t, so to the power of 1 by 2. So let me just write this. So this will be d omega t whole to the power of 1 by 2. So using this I can calculate. So let us go back to the waveform. Let us see the other observations which you have to make here. So here you can make the observation. First one is the current is rising to the peak and it is falling. So after this point pi, that means after the point pi, you can see here your output voltage is negative, but the current is positive. What is the meaning of this? The power is the product of voltage and the current, it is coming as a negative. The meaning of this is the inductor, the energy stored in the inductor is now fed back to your supply. During this much time your power is negative, that means it is fed back to your supply. And the second one, the output voltage is having both the positive component as well as the negative component. And the second one, the current waveform is not smooth, because the purpose of the converter is I want my output should be as pure DC as possible. So that is missing here, that is missing here. So how to improve this one? And second one, how can we bring that the thyristor is turned off at pi itself? That means the thyristor is not extending its conduction up to beta. I want to stop the conduction of the thyristor at pi itself. So how can I make it so that that negative voltage will not be there? So that can be achieved by using a freewheeling diode. So that we are going to see in the next topic. So that is single phase half wave control rectifier with RL load and the freewheeling diode. So I have connected one freewheeling diode like this. So during the normal operation, whichever is done at alpha we are firing, at angle alpha we are firing. So at the instant when you are firing this, you can see here this Vs, upper plate is positive, lower plate is negative. So this thyristor is forward biased. As the thyristor is forward biased and you coming to this freewheeling diode, across this freewheeling diode what is there? This Vs negative is connected here, plus is connected here. That means the freewheeling diode is reverse biased. That's why freewheeling diode will act as the open circuit and only your thyristor will be forward biased. So at the instant when the firing angle alpha it is triggered, so the output current will start. So when the current start passing, this freewheeling diode is reverse biased. So the current will pass from your source to your load. The current is supplying from source to your load. So now what happens at omega t is equal to pi, if you are drawing the output waveform, let us try to draw the output waveform. Let us assume at the instant V0, so the output voltage is like this. So this output voltage is applied across the freewheeling diode. That output voltage is reverse biasing the freewheeling diode, it is not conducting. But at omega t is equal to pi, just when you are increasing, the output voltage is becoming negative. When the output voltage becomes negative, negative means lower side positive and upper side is negative. So this diode get forward biased. That means at omega t is equal to pi plus, this freewheeling diode gets forward bias. When the freewheeling diode get forward biased, what will happen? It will short circuit your output, so your output voltage will become 0. So your entire current will start circulating in this loop. Entire current will start circulating in this loop for omega t greater than pi. So after that, the freewheeling diode will start acting. So what happens? Your output voltage will be 0 after pi. Again, from this instant, that means whenever the firing angle is there, so when it is fired, again at this instant it will be there. So let us take the case of continuous conduction mode. Continuous conduction mode means because there is a path for your output current to pass through this one, let us assume the current is continuously passing. So I am taking the instant, at this instant the current is equal to I naught at the instant of alpha, and then gradually I am going to make the derivation for the same soon. So at this instant, let us assume this current is equal to I1. This is at omega t is equal to pi. This is at alpha. So it will gradually decay, and it will decay up to the value again I0. So again what happens? Again it will rise and it will fall. So this way output current is coming. So let us try to derive the equation for the same and prove that current waveform will be like this, and then we will proceed further. So that's why from here we can tell that the operation of the circuit can be explained in two modes. One is the conduction mode, during which the SCR conducts, that is from alpha to pi, and second one is a freewheeling mode, during which the freewheeling diode is active and automatically the output voltage is equal to 0. So first I am starting with the conduction mode. It will be from the firing angle alpha to pi. So where your thyristor is forward biased, so it will conduct. So I can write the equation again, same thing like before. Vs is equal to I naught multiplied by R plus L into di naught by dt. Again this will have two components, one is steady state component and transient component. So from previous section I am writing directly. This is V maximum by Z sin of omega t minus pi plus A e to the power of minus R by L into t. So we have to find the value of A based on the initial boundary conditions. So here in this case, at omega t is equal to alpha, previous case it current is 0, but here we are taking the continuous conduction mode. So for continuous conduction mode, I naught, let us take it as a small I naught. So if it is a non-continuous conduction mode, in that case I naught will be 0 like before. So I am taking both the cases so that how to derive will be clear to you. That's why I have taken two different cases here. So now I naught, if I are substituting these boundary conditions there, I naught, small I naught will be equal to capital I naught is V maximum by ZZ into sin of omega t. I have substituted alpha minus phi plus A e to the power of minus R by L into t. So omega t is equal to alpha, so t becomes alpha by omega. I have substituted that one here. So from this I have calculated the value of A, and that I have substituted in the original current equation. So if you substitute in the original current equation, it is coming as V maximum by Z into sin of omega t minus phi plus I naught minus V maximum by Z sin alpha minus phi into e to the power of minus R by L into t minus alpha by omega. Like this type of equation came. So that's why your current will pass. So now coming to the second mode, freewheeling mode. Because we know after pi, the freewheeling diode will be forward biased and it will act as a short circuit. It will allow the dissipation of the energy that is stored in the inductor. Because inductor will not allow the sudden change, so it will start supplying the current. So it will act as a source now. So now the freewheeling diode is forward biased and automatically the value of output current will be equal to IFD. So automatically the current taken from your source will be equal to 0. As the current taken from your source is 0, your SCR get reverse biased and SCR will stop conducting. It will act as an open switch and your output voltage is equal to 0. So now applying the KVL, So again, because we know the output voltage is equal to 0, this will be equal to R into output current plus L into di naught by dt. So from this I can write, because last section we have derived, so I am directly writing I naught is equal to A e to the power of minus R by L into T. So I have to derive this value of A in this mode. So we know that at omega t is equal to pi, let us take value of I naught, that means output current is equal to I01. So this I01 I am substituting here and substituting t is equal to pi by omega. I got this. So I got the value of A. When you substitute it, you will get it output current I0 will be equal to I01 into e to the power of minus R by L into t minus pi by omega. That means after this instant it will go on decaying. That means what we can tell, during the freewheeling mode the current is continuously decaying, whereas in the case of normal mode or the conducting mode, the current will gradually rise up to certain extent, after that it will start falling. That means it will gradually rise at some peak, that peak will come before pi, it is not rising after pi. So let me try to draw it properly so that it will be clear. So it will reach up to some peak here and it will start falling, and generally this angle will be always greater than pi by 2. At that angle it will happen. So let us try to draw the waveforms for the remaining. So out of this I naught, this freewheeling diode is supplying when your thyristor is not conducting. We know the thyristor is conducting from this instant, that means alpha to pi your thyristor is conducting. So this is your thyristor current or your source current. Similarly again here also it will conduct from here to here. This is your source current as well as the current passing through the thyristor. So remaining current, output current is supplied by the freewheeling diode. So freewheeling diode waveform will be like this. Again it will start from here. So it will gradually decay up to here. So whatever the waveform slope is there, the same thing will come here. Was not able to draw properly. So this will be like this. Getting it? So now coming to voltage across the thyristor. Voltage across the thyristor, we know from pi onwards the thyristor is acting as an open switch. So automatically from here omega t is equal to pi, it is reverse biased up to 2 pi. So after that it is in the forward blocking mode. It is in the forward blocking mode. So this duration is called as the circuit turn off time. In this case the circuit turn off time is because your thyristor is turned off or this reverse biased for a duration of Tc is equal to pi by omega, because it is reverse biased from pi to 2 pi. From here to here it is reverse biased. Getting this one? So let us proceed further and try to analyze the remaining things. So proceeding further, so during the freewheeling mode, the energy stored in the inductor is supplied to the load resistance, therefore more power is delivered to the load for the same firing angle. Because the energy that is stored in the inductor is now supplied to the resistor, it is not opposed by anything, it can easily pass. So automatically as the more power is supplied for a given input volt amperes, because for a given, because input is supplying only for some duration, remaining duration the energy stored in the inductor is supplied to the resistor. So in that mode we are getting the continuous current, that is the second advantage. So automatically load current waveform is improved, and the second one, the energy stored in the inductor is efficiently used for the conducting, so automatically the converter efficiency will improve. And coming to the input power factor, we know the input power factor is the ratio of power delivered to the load divided by input volt amperes. Input power factor is power delivered to the load by input volt amperes. Now for a given input volt amperes, the power delivered to the load is more in this case because of adding the freewheeling diode. So automatically input power factor improves. If you have doubt about this, what are these converter efficiency, input power factor and other things, you can please refer to my performance parameters I have discussed for semi-controlled converters. So same definitions apply here also as well as the formulas. So only difference is there the firing angle is equal to 0 because we cannot control the firing angle, but for controlled converters we can control the firing angle. That is the only difference. So I hope everything is clear up to now. In the next class we are going to discuss about RLE load, and followed by we will try to solve 1-2 numericals so that this
So this is the class for working of single phase half wave control converter using of RL load and RL load with using of freewheeling diode. So this is the class of today. We have the few quiz questions and frequently asked questions. So next class we are going to discuss about the single phase full wave control converter using of R load. Thank you.